Continuing our discussion on the inertial motion, we left off here and looked at the Rossby radius of deformation and the inertial period. Going to our equation, x minus b over f squared plus y plus a over f squared. So these came from the momentum equations where we dropped the pressure gradient terms and looked at the what is called aqua planet, where the entire globe is an ocean. Inertial scale, as we said, is proportional to 1 over f, should decrease with latitude and become singular at the equator. And we looked at the inertial period. Then 2 pi r, where r is now the Rossby radius of deformation, is 2 pi cp over f. So this is gravity wave speed times the inertial period, which is 1 over f. So essentially it becomes an issue of how far a gravity wave can travel within one inertial period. That is the Rossby adjustment problem, or the geostrophic adjustment problem. So here is a nice example of an inertial circle in the Baltic Sea. We'll come back to this later on in the tropical context, where these are looking at days. So the motion is set off and then typically happens below the surface. So the wind forcing is strong enough to create motion within the thermocline at, let's say, several hundred meters below the surface, because near the surface there is always wind and that's going to perturb the motion. But below, weak winds will not reach, but strong winds can set off a motion, and then the wind burst, or the strong wind will die off, and then normal winds will settle in. But this motion will continue because there is no friction. So you can see the days 18, 19, 20, and 21 and so on. So it keeps going with the mean current. Obviously there is a mean current as well. So this is a real phenomenon, easily observed in the slow moving heavier ocean, but not so easily seen in the atmosphere, even though it can be seen in some quiescent periods in quiescent places. Rossby radius of deformation is then the distance a gravity wave travels during one inertial period. There are other interpretations we will see where the Rossby adjustment becomes about how far the cold polar air can come in down into the low latitudes where the near surface densities are lower and so on. But we will go into that much later on. For a shallow barotropic fluid of depth h, we wrote r as c over f, or square root gh over f, and in a baroclinic fluid we wrote it as ng over f with the Brunt-Väisälä frequency and the scale height of the atmosphere. So let's look quickly at how the adjustment depends on the scale of the perturbation. So assume that we have a latitude band where the system is in geostrophic adjustment, and you somehow created a perturbation, a mass perturbation. You piled up a mass somehow, let's say by having a wind stress curl that created a convergence and piled up, and then it disappeared. So then the question is, how will this mass adjust once the perturbation is released? That depends on the scale of the perturbation, because that is the essential Rossby or geostrophic adjustment problem. So if the length of the perturbation is much smaller than 2 pi r, then buoyancy effects dominate. So you had raised the fluid, gravity is going to pull it back, and that's the buoyancy effect, and the initial potential energy is going to just radiate out as gravity waves, and ultimately at some time t0 the surface is going to become flat again, so the waves just dispersed away and then dissipated after whatever scale they had the energy to go to. If, on the other hand, the perturbation is so large that it is greater than 2 pi times r, where r is again the Rossby radius of deformation, which depends on the equivalent depth, it depends on latitude, and so on, then the potential energy is so large that initial gravity wave dispersion does happen, but the time scale is long enough that the Coriolis begin to act on it, and the winds begin to adjust to the mass field. The mass field is so large that the winds begin to adjust. So the finite hump then doesn't completely dissipate away, because the winds adjust and create an anticyclonic inertial motion which tends to maintain the original perturbation to some extent. Imagine the anti-cyclonic circulation in the northern hemisphere. Curl your fingers, you have the arrow going in, so you put the finger in and you have arrow coming out, and the finger points upward, so you have anticyclonic motion, convergent motion, pushing the water down and keeping the sea level up. Okay, this is the Rossby adjustment problem. Essentially, you have to remember that it depends on the scale of the perturbation in a idealized system that we imagined here. As we saw, inertial motion does happen in the real world, and these kind of Rossby adjustment problems also are real in the real world. But in the ocean, because the ocean is slow moving, has very low Rossby number everywhere, and hence can allow you to observe these phenomenon happening at large enough scales. And they are captured by buoys that are floating around, or sometimes satellites that are observing sea levels, blobs moving around, and so on.